So, welcome student to the next class of introduction to nonlinear optics and its application. This is lecture number 30. So, in the previous class we have learned something about the quasi phase matching, mainly the calculation part. In quasi phase matching, the important thing is that we have an arrangement where the value of D is periodically changing. Here the periodically changing means the sign of D value is changing periodically from +1 to -1. So, now we will going to calculate and try to find out that once we have this kind of function in our hand, how this can affect the evolution of the second harmonic and the phase that is created due to the phase mismatch, which is a delta k term k2 minus 2 k1, how it is compensating that term, that we will going to calculate today. So, today we have two topics to discuss. One is calculation of quasi phase matching and second is realistic calculation of second harmonic generation. So, realistic calculation of the second harmonic generation is a different part that we will start today, but let us first find out what is the quasi phase matching calculation. So, if we see that the quasi phase matching, for quasi phase matching the D is now function of Z, that is the important part. The equation of second harmonic, whatever the equation is written here in this slide, is exactly the same that we have already derived previously. Only important inclusion here is now D is function of Z, that means there is a variation over D. If D is a periodic function, then we know that D can be written as this form. We used this in the previous class. Dz can be represented in this particular form, Gm e to the power of I m kq z, where m goes to minus infinity to infinity. Once we write this dz, then readily we have an expression or the relation over D, which suggests that over a period lambda D has the same value. Since we have this condition, I can write D in this particular form. We have already proved in the last class. If we use this value, here, the value of D, then we can write in total it is Gm e to the power I k q minus delta k because of this minus I k term and Z over sum. Now, once we have this, I can expand this term as a function of m by changing the value of m. So, d2 d e2 dz I d0 omega c n2 e1 square, this is the constant term, and then I expand this term. So, first term if I put 0, this term will be 0, this term will be 0. So, z0 e to the power I delta k z, that is some sort of term that we already had. This is if there is no k q, then we will get some term like this. Now, this from the second term the contribution of k q is there. So, if I put m equal to 1, we have k q plus delta k z. If I have k m equal to minus 1, I should have z of minus 1 e to the power I k q plus delta k z and so on. If I write what should be the term for m equal to 2, it should be g2 e to the power of I 2 of k q minus delta k z. What should be the term of m equal to 3? It is G3 e to the power of I 3 k q minus delta k into z and so on. For the negative case, I just put a negative sign here. When I put a negative sign, I need to put a negative sign. So, this negative sign and this negative sign I can take common, then it should be minus of I 2 k q plus delta k z when m equal to minus 2 and so on. So, this term will go on. Okay. So, the next slide, if I go, this is the expansion of dE2 dz. Now, the next step is to find out E2, that is our goal, but before doing that I need to make some comment here or try to draw your attention that here in G1 term we already have, here in G1 term we already have a phase which is kq minus delta k. This is the phase that already there. If I forget about the quasi phase matching term, if I write only the second harmonic generation term E2, this differential equation term, it was initially I of d of omega divided by n2 c e to the power E1 square, and the phase term was e to the power of minus of I delta kz. This was the term that we have without any kind of periodicity. D was only a constant term. So, the first contribution, if I see the first contribution of this term is something like this, but here D0 and Z0 are the two terms which is basically this D term, a slightly modified kind of D. But from the second term onwards, what happened that we have a term in phase which is related to kq. That means there is the first case, what was the phase matching? Delta k equal to 0 is the phase matching condition, but for the second case the phase matching condition appear when kq is equal to delta k. That means phase matching condition is now with kq term. So, kq is included, and then here also we have some sort of phase term, but kq equal to minus delta k is our phase matching. In the similar way, if I go on with higher values of m, then the next higher order term is G2, which we have already shown that here the condition of phase matching is this. So, 2 kq minus delta k equal to 0 is our phase matching, this is delta, our phase matching. Well, so once we have this expansion, the next thing is to integrate it. So, if I integrate, we know what should be the value. For the first case, it is some sort of sine function. So, sine divided by sine delta k z divided by 2 delta k by 2, this is the old term that we have already calculated. Second term, we will have exactly the similar form, only delta k will be replaced by kq minus delta k. So, we will have again have sine of these things, and then okay, here we have a mistake, it should be kq, this z will be outside. So, here also this will be outside, kq delta k multiplied by z. So, we will have a sine term also here and so on. After integration, the next thing is what happened, we will put our phase matching kq is equal to delta k, that is a phase matching, that is a quasi phase matching, we call the first order quasi phase matching. So, when we put kq equal to delta k, then you can see readily, you can find that only the major contribution will come from this term. Here if I put kq equal to delta k, this term will be sine of kq z by 2 divided by kq by 2. It will not going to get any high value because it is some sort of sine function, or if I write in terms of kq, it is a sinc function. So, we know that the sinc function got a maximum when these and these are 0, tends to 0, but here we find that it is not the case. What about the other terms, the higher order terms? The higher order terms, for example, if I write g minus 1 and put kq is equal to delta k, we eventually have a term e to the power of minus I 2 of in in terms of sine. After integration we will have a sine term. So, we will have g of 2 sine, this term will be 2 k q and minus k. So, minus k will be represented by plus minus k q, minus delta k is represented by minus k q. So, we will eventually have sine of k q divided by some term which is again k q. So, again we will find that this term will not going to vanish because k q is equal to delta k, it is not 0. Only contribution we will have this, and this term tends to 0, this term tends to 0 and this term tends to 0, that means this term tends to 1 when we have k q is equal to delta k. Under that condition I can write E 2 is approximately equal to I d 0 omega c into E 1 square, which we already have, multiplied by the coefficient g 1 and the limit at k q minus delta k tends to 0. This limit basically gives is z. So, we will have a z here. Now, g 1 is this, because g m is equal to 2 divided by m pi sin m pi d. So, g 1 can be represented in terms of this quantity. So, g 1 is 2 pi, if I put m equal to 1 it should be 2 divided by pi sin of pi d, because m is 1. And now, if I say my duty cycle d is equal to half, then it should be 2 divided by pi, because d half means sin of pi by 2, it is 1. So, we have d half. So, if I now write this g 1 and d 0 together, we will have an effective d. This effective d is nothing but d 0 divided by 2 pi. So, we can see that the first contribution, which is containing g 1 term, in this case this d effective is less than d 0 by a factor, because d effective is d 0 multiplied by 2 by pi and pi is 3.14. So, that means we will have a quantity which is less than 1, that is multiplied to d 0. So, d 0 is reduced a bit, but we still have a contribution, and this contribution basically give rise to second harmonic. All the other contribution will not going to give any kind of phase matching. So, this term will die out very soon. So, only term that will be there is this. So, if I now try to find out what are the other possibilities of phase matching, then k q equal to delta k is not only the one phase matching condition that one can have in this quasi phase matching, but 2 k q is equal to delta k, that is another one, 3 k q is equal to delta k is another one. So on I will find the higher and higher order phase matching. But you have to be remember that if I, for example, we can have a system where 2 k q equal to delta k is our phase matching condition, then which is the term that is responsible is our G 2. Now, if I try to find out G 2 with the duty cycle D is equal to half, then G 2 is what was our G m? G m was 2 divided by m pi and then sine of m pi multiplied by the duty cycle D, that was the form of G m. Now, suppose we have second order phase matching. For second order phase matching, the value of m is 2. Now, I try to find out what is my G 2, because G 2 will be affecting on generating of the second harmonic. So, G 2 will be 2 divided by 2 pi, because m is 2, and then sine of 2 pi multiplied by D. This first term 2 will cancel out. So, we will have 1 by pi sine of pi, because D is half, but sine of pi we know that this is 0. sin of pi is 0. That means, even though we have a second order phase matching condition, we can have G2, but the contribution of the Z2 is 0. So, second order phase matching, the contribution of Z2 is 0, that means we will not going to get any kind of second harmonic generation, even the phase matching is there. Be careful about that, because the coefficient G2 will going to vanish. Why it is vanishing? That is interesting, and it is vanishing because of the D value. We are using this duty cycle equal to half, but the duty cycle D is represented by L divided by big lambda. Now, if I say L divided by big lambda, this ratio is 1 by 4, because this is in our hand, then you can readily find that D is 1 by 4 and this value is pi by 2, and then again you start getting G2, because here the G2 is not equal to 0, but 1 by pi. So, in order to excite the second order quasi phase matching condition, the important thing that you need to take care is the duty cycle. If you change the duty cycle, there is a possibility that you will get G2 not equal to. If you retain with the previous duty cycle, that is half. So, with this periodicity, what happened, you will not going to get any kind of second order quasi phase matching, even though the phase matching is there, but the effective contribution will be 0. So, next here we will going to conclude our topic. Okay. So, before that we have something to say regarding the vector diagram. So, in vector diagram, this is a collinear kind of phase matching. If I write this vector diagram, so you can readily see that K2 delta K is equal to K2 minus 2 K1, and if I write the first order, it is Kq minus delta K is equal to 0. So, delta K can be in the vector diagram can be represented is this, and this Kq is basically the vector which is associated because of the periodicity that is there because of the periodic D function. So, after that, this is the end of the study of quasi phase matching. So, now we will going to start a new topic, which is the realistic calculation of second harmonic generation. So, this realistic calculation was important because in the realistic calculation we will not going to consider the electric field having the frequency omega, or the fundamental electric field is constant, because it is also changing. We have two coupled equation. So, if I see this equation, so let us go back to the equations. So, under phase matching condition delta K equal to 0, we have two equation in our hand, if you remember. Both the equations are coupled to each other, and in order to find out K2, initially what we have done, we take this E1 as a constant and then integrate. When we integrate, we find that E2 is proportional to Z, or the power is proportional to Z square. So, when we put the efficiency curve, it was like this, but we also mentioned that this is not realistic. So, over Z, eta of Z was something like this, but we also mentioned that this is not the correct representation of this efficiency. So, we need to find out the realistic calculation. So, now we will going to do that. In order to do that, what we do is we divide the total electric field E1 into two part. One is amplitude part U1 Z, and a phase part U e to the power I phi Z, phi 1 Z. So, both are now varying with Z. For E2 also we will divide into amplitude and phase in this way. Once we have the amplitude and phase separately, where U1 and U2 are the real quantity, also phi 1 and phi 2 are the real quantity. This complex amplitude we can always divide into e to the power I r e to the power I theta form. So, here it is something like this. So, now we will have a derivative over E1. So, when we make a derivative over E1, so since E1 is represented by E1 e to the power I phi 1, so the derivative of U1 and phi 1 can give this form, d U1 dz plus I U1 d phi 1 dz e to the power I phi 1, and this quantity is in from the right hand side I write it is I d omega c n 1 and E2 E1 can also represent in terms of E1 and E2, U1 and U2 multiplied e to the power I phi 2 minus phi 1 because there is a star. So, that is why minus phi 1 is there. So, this phase is associated with that. So, in the left hand side we have d u1 dz plus I u1 d phi 1 dz I d omega c n 1 u1 u2 e to the power I theta z, where theta is phi 2 minus 2 phi 1. This is the phase difference between these two, but not the total phase difference. This is some quantity phi 2 minus 2 phi 1. The phase difference should be phi 2 minus phi 1, but 2 term is here. Now, the amplitude equation, we had an equation here. If you look carefully, this is our equation. So, this equation is a complex equation. So, in the left hand side the real and complex. So, we know that if 2 x plus I y is equal to a plus I b, then we can write x is equal to a and y is equal to b. We will going to use the same thing, the real part of the left hand side will equal to real part, and if we do, we will find this equation that d u1 dz is equal to u1 u2 sin theta multiplied by d omega c n 1, and the imaginary part which is again equal, and the phase equation I will get this quantity. In the similar way, we can find the same thing for E2, and I will not going to explain the entire process because it is already there. So, I ask the student to do these things by yourself to find out these two equation for E2, and you will find that you will get these two, all the calculations already there, but I will still ask you to do that by yourself. This is a very straightforward calculation. So, real and imaginary part you can extract out from these two. So, after doing all this calculation, when we extract the amplitude and phase equation together, then the next thing we can do is to use this thing. Now, if we use that this d omega c n 1 and d omega c n 2 are very, if n 1 and n 2 is very close to each other, we can write d omega c n 1 and d omega c n 2 very close to each other, and we write as general coefficient kappa. So, when I do that, then we will find these things will reduce the calculation significantly. Now, two amplitude equation I can write d u1 dz is equal to minus kappa u1 u2 sin theta, and d u2 dz is kappa u1 square sin theta. This was the two amplitude equation. Mind it, the term kappa is used in two different cases because d omega c n 1 we assume n 1 is very close to n 2. So, we assume that they might be same. For amplitude case also we have amplitude equation, and this amplitude equation is u1 d phi 1 dz is equal to k u1 u2 cos theta, and u2 d phi 2 dz is equal to kappa u1 square cos theta. Now, we know theta is equal to phi 2 minus 2 phi 1. So, when we make a derivative of theta, we will have an additional term d phi 2 dz minus 2 d phi 1 dz. Phi 1 phi 2 we can have from here. When I use this phi 1 phi 2, we will have an expression of d theta which is u1 square u2 cos theta minus 2 kappa u2 cos theta. Why we are doing all this calculation we will find in the right hand side basically, because in the right hand side eventually we get one quantity which is conserved over the distance. That means, it is not going to change. To figure out, we need to use this methodology, this calculation, and in the Boyd book this calculation is there. If somebody is interested, he or she can go to this book, but all the calculation is here in this slide. If you do this calculation by your own, then you will find that it is not a very critical calculation, rather it is a lengthy, but it is not a very critical, it is a straightforward calculation. Next, we will find one very important quantity, and that is log u1 square u2. When we try to find out log u1 square u2, if I make a derivative of z, 1 u1 u2 is be there because I am making derivative. So, u1 square, then the derivative of this quantity which is u1 square this plus the derivative of 2 u1 u2. So, we will have this. Again we will going to use this d u1 dz and d u1 dz from this equation, these two equation, and we will find one expression like this. If I simplify this equation, we will eventually have one expression d dz is equal to log of u1 square u2 kappa sin theta divided by u2 and u1 square minus 2 u2 square. Now, in the right hand side, this quantity we already get here in terms of theta. If I slightly manipulate this thing, this cos theta and all these things, I can write d cos theta by z divided by, if I put this cos theta here. So, 1 by cos theta will be this term, and now sin theta is multiplied, sin theta by cos theta d dz is equal to log of d dz of ln of u1 square u2. These two quantity, this quantity can again be represented as log. So, minus of d dz ln cos theta should be equal to this quantity. If you look carefully, you can readily understand what is going on. Now, if I combine these two, the important, very important expression that will come is d dz of ln u1 square u2 cos theta is equal to 0. That means, u1 square u2 cos theta is equal to constant. This is a very, very important expression that we end up, that u1, u2 and cos theta both are varying independently, because u1 is the amplitude of the fundamental wave, u2 is the amplitude of the second harmonic, and theta is a difference between their angles, difference between their phases, but the phase directly it is not difference. So, theta is phi 2 minus 2 phi 1, phi 1 and phi 2 are their phases. So, theta is difference of these two quantity, but they are also changing with respect to z, that means theta should be a function of z. So, u1 u2, so if I now write u1 u2 cos theta is equal to constant. So, this means u1 which is a function of z, u2 which is a function of z, cos theta is a function of z is constant. Now, if I put some boundary condition, if I put some boundary condition, E2 at z equal to 0 is 0, because at the beginning there was no second harmonic. So, that means U2 at z equal to 0 has to be 0. When U2 at z equal to 0 is 0, that means U1 z, U2 z cos theta equal to 0 constant, which is same as all the term at 0 point. So, U1 0, U2 0, cos theta 0, that should be equal to this quantity, because it is a constant throughout the motion. But now we find that this quantity is 0. That means, whatever the constant we are try to say is 0. That means, U1 square U2 U1 to z, U2 z and cos theta z is 0. Now, again we find a very interesting outcome from this. U1 and U2, U2 is 0 at z equal to 0, that is true, but after that U2 is not equal to 0, U1 is also not equal to 0, this is multiplied by cos theta and this entire quantity is 0. It is only possible when the theta has some relation. So, theta z which is phi 2 z, 2 phi 1 z, if this quantity is plus minus pi by 2, then only we can say that this is a valid equation. So, we find a valid equation here, and this valid equation suggests that when they have a phase relationship, so that means when the second harmonic is generating, there is a phase relationship between the second harmonic and the fundamental wave, and this phase relationship is phi 2 minus 2 phi 1 is equal to plus minus pi by 2. So, we will in the next class we will going to use this phase relationship to find out what is the parametric generation and all these issues will come. But important thing is this calculation is lengthy, but important thing is one quantity that is conserved during the propagation is u1 square u2 multiplied by cos theta, and this cos theta is something where theta is represented by the phase of the fundamental and second harmonic wave. This phase relationship phi 2 minus 2 phi 1 and phi 2 minus 2 phi 1, this phase relationship is maintained throughout the distance. So, phi 2 minus 2 phi 1 is always plus by minus pi by 2 depending on the situation, and then it is conserved throughout the propagation. So, we find a very important outcome today, that one equation that is not changing, and using that we will find out what should be the amplitude and phase evolution over the distance, and we will find in that case that it is not a z square dependency, but we have a realistic calculation. So, with this note, let me conclude today's class. So, in the next class we will start from here and try to find out more about the second harmonic generation and how the second harmonic field will going to evolve under realistic condition, that we will going to find using today's outcome. So, with that note, let me conclude here. See you in the next class, and thank you for your attention.